this video, we're going to go a bit beyond the empirical formula to now look at how we would do something for a molecular formula calculation. So to calculate a molecular formula from the empirical formula, you need some additional information about the molecular molar mass of the compound. There's my pointer. So if this information is provided, you can take the empirical formula mass and calculate it from the empirical formula the same way we determined it in the last couple of slides. So once the two pieces of information are known, your empirical formula and your molecular formula molar mass, we can use this formula. The molar mass of the molecular formula divided by the molar mass of the empirical formula gives you a factor known as N. So N is the ratio of what we need to multiply by all the numbers by to get to a molecular formula. So for example, let's say we had the compound CH2 and we calculated the N was equal to 3. Then the molecular formula for that is going to be C3H6. So let's take an example of this now and give it a try. So I want you to try this problem. We give you an amount of carbon, hydrogen, and nitrogen, and we tell you the molecular molar mass. I want you to determine the molecular formula, and if you're not sure how to do this, at least get to the step where you find the empirical formula. Note that you can find the molar mass of the empirical formula and use that here, but if you're uncertain, just stop at that step, and I'm fine with that. So give it a try now. So let's take a look. So step one of any of these problems is find the empirical formula first. So we have 39.97 grams of carbon. We change it to a percentage. And its molar mass is 12.01 grams per 1 mole of carbon. We also have 13.41 grams of hydrogen. Every 1.01 grams of hydrogen is 1 mole of hydrogen. We then have 46.62 grams of nitrogen. And for it, it's every 14.01 grams of nitrogen is 1 mole of nitrogen. So we're going to take all of these and find our numbers. So 39.97 divided by 12.01 is going to give us 3.33 moles carbon. We have 13.41 divided by 1.01. That's going to give us 13.28 moles hydrogen. We have 46.62 divided by 14.01. This is going to be 3.33 moles nitrogen. Now we'll divide all of these by 3.3. 3.3, 3.3. From there, we have 1 carbon. We have 13.28 divided by 3.33. We have 3.99 hydrogen, and we have 1 nitrogen. As a reminder, we said greater than 0.9 we could round, so I'm just going to round this to 4 hydrogens. So our empirical formula is CH4N. So if it asks for the empirical formula, you could box it and you would be done. But it asks about the molecular formula, and it gave us a molar mass for the molecular formula. So we need to find the empirical molar mass. So our empirical formula mass, remember, it's going to be related to these atoms. So we need to add 1 carbon, 1 nitrogen, and 4 hydrogens. So each carbon has a mass of 12.01, the nitrogen has a mass of 14.01, and 4 hydrogens have a total mass of 4.04, which is 1.01 times 4. We get that this empirical formula has a mass of 30.06 grams per mole. So N is going to be 60.10 divided by 30.06 grams per mole. And we get that N is equal to, so we have 60.1 divided by 30.06. I got 2.00. If N is not an exact integer, let's say you got 2.1, you should always round N to a whole number, since we can't have a ratio, you can't have something like 2.5 atoms in our molecule. So in this case, it came out nicely, but if it was 2.1, just round that to 2. Or if it was 1.86, round that up to 2. Or if it's 2.95, round that up to 3. So to get the molecular formula, we just take this value and multiply it by each atom. So in this case, we have C2H8N2. And that is our molecular formula, and finishes up our material on being able to calculate these formulas. So where we're going to go at from now is we're going to talk about naming compounds a bit and types of bonds. For this video, I'm going to limit it to just talking about the types of bonds and mostly ionic bonds. And then in the future, we're going to go into actually how to name these things. The reason why we're talking about these together is based on the type of bond determines how you name stuff. So our compounds are made of atoms, and we hold them together via chemical bonds. Different types of chemical bonds are going to hold atoms together in different ways. And as such, they're going to have different properties, so we'll talk about them differently. The chemistry is different. Compound naming rules are going to be based on the type of bond used to hold the compound together. So in this class, we will work on naming compounds bound together by two different types of bonds. I mentioned this because there are other types of bonds for atoms for compounds as well, but we're going to stick to these two. Ionic bonds. These are going to be bonds that occur primarily between metals and nonmetals. And covalent bonds. These are primarily going to be bonds that occur between nonmetals combined to other nonmetals. We'll talk about some times where this isn't the exact rule, but this is the best general case of how to talk about this. So let's talk about ionic bonds in this section. So when a metal interacts with a nonmetal, it can form an ionic bond. It does this by transferring one or more electrons from the metal atom to the nonmetal. So the metal atom becomes a cation since it loses an electron. The nonmetal atom becomes an anion because it's going to gain an electron. So remember, our nonmetals are in the top right part of our periodic table. They really like having electrons. They have things like high ionization energies. They also have electron affinities that tend to be really negative. It's very easy for the nonmetals to gain electrons, whereas they really don't want to give them up. Metals tend to occur in the bottom left. We know from ionization energy it's very low. They're easier to remove electrons from. This is the reason that in an ionic bond between a metal and a nonmetal, the metal is going to lose an electron, where the nonmetal gains it. Since they're now charged because they lost and gained electrons, they form anions and cations, and they're going to be attracted to each other since opposites attract. So now, how are we going to represent this and draw this? We're going to talk about Lewis models here. So the Lewis model is used to represent the valence electrons around the atom, and we're mentioning this here when we talk about where electrons go. So for example, oxygen has 6 valence electrons. We represent this with 6 dots. So as a reminder of where I got that from, oxygen's configuration is 1s2, 2s2, 2p4. Everything with this 2 right here is valence. And so we represent those with dots. Each dot is going to represent 1 valence electron around the atom. To draw a Lewis structure for an individual atom, dots are placed one at a time around the atom, and then doubled up after a dot is placed on each side. So we place the 4 dots first, and then if we have more, we start pairing them up. Let's see. Oh, and the goal generally for our atoms is they're going to try to get to either 8 dots, because then they're going to have a noble gas-like configuration, or 0 dots, because by giving up all their valence electrons, they then have they're now in a noble gas as well. So how do we use this to talk about ionic bonds? So Lewis theory is mostly can be used to talk about ionic bonds. We're going to use it a lot more to describe covalent bonds. So this is going to come back up. So especially if you've ever heard about Lewis structures before, we'll do a lot more talking about them. We're going to talk about them very basically here, but we'll do more with them, don't worry. So when atoms bond, they tend to gain or lose electrons to reach our noble gas configuration. So what that looks like is the noble gas, it's going to take on some form of S2P6, with the exception of atoms in the first row, because that's where you don't have a P. So helium, for example, is just 1s2. It stops there. But anything after that, once you start getting down to neon, you start having atoms that are going to reach towards this NS2-NP6 configuration. So 2 examples. The sodium atom. Sodium is a metal. It's in the alkali metal group, so it's going to tend to form +1 cations. And this is sort of an explanation of why. You have Na, which is 1s2, 2s2, 2p6, 3s1, and if it loses 1 electron, it becomes 1s2, 2s2, 2p6. You'll notice this is the noble gas configuration. And if we were to write sodium as an atom, it would have 1 dot. If you were to write Na+, we wouldn't have to worry about any dots. It lost its last valence electron. Now, for chlorine, it's got 3s2, 3p5. It's going to have 7 dots. And I'm not worried about what order you draw the dots in as long as it's got 7 and not 8. Now, if it were to gain an electron and form Cl-, then Cl- is going to have 8 dots. And so now it's going to have a full octet because it has this 3s2, 3p6. So using these models is one way to think about them, is to think of, oh, what does it look like? How does it get to 8 dots or how does it get to 0 dots? So yeah, these are the pictures, just I'm drawing them using the Lewis model. Okay, so one last thing I've got to talk about is crystal lattices. I didn't mean to put this all up on the page at one time. I know that makes it harder to go because you want to read everything as you go, but try to stick with me. So ionic compounds contain positively charged particles, we call those cations, and negatively charged particles, we call those anions. That's just a review. We've got cations and anions together. Since we have positives and negatives, they're going to be attracted to each other. And the structure they take in the ionic compounds is going to be something we call a crystal lattice. And what that means is that each cation is going to be surrounded by a bunch of different anions. And each anion is going to be surrounded by cations. So for this reason, when you have an ionic compound, it's going to be surrounded by lots of different ions. It's not just one. So this means there's not an ionic molecule, but instead a large lattice of many cations and anions bonded together. So for example, if you think of sodium chloride, you have Na plus and Cl minus. You don't just have 1 plus and 1 minus though. This Na plus has Cl minuses surrounding it on different sides. And it's not just in 2 dimensions. You also have some like going out of the screen and into the screen. And they're different. And when you get to 1212, we'll talk about the exact shapes these take on. There are different reasons why some molecules will take different shapes, and we'll learn about them. But for now, we just want you to know that they make these 3-dimensional structures. They're huge. There are lots and lots of ions all connected together. They're not discrete. It's not like there's one sodium and one chlorine and they're connected together, and there's another sodium connected to one chlorine. The way the shapes come about is they serve to maximize the attractions between the cations and anions. So we allow each ion to be around as many possible other ions while accounting for others. Because you notice while I drew a lot of chlorines around that sodium, there are also going to be sodiums on other sides of the chlorines as well. So these things expand in all directions in 3 dimensions, and so they try to just pack everything in. So the way to think about this for ionic compounds is to think about the simplest ratio for the formula unit. You'll notice this sounds a lot like, hey, empirical formulas. We're not going to talk about molecular formulas when we're doing ionic compounds because they don't have a discrete number of atoms. Our other types of bonds, we will see that. Like water molecules don't work like this. There are a very specific number of atoms in them. But when you're dealing with ionic compounds like sodium chloride, there are just lots and lots of sodiums and lots of chlorines. They're on the order of moles sometimes. Or even if it's not quite a mole, it's still in a rather large number. It will be more than trillions of ions connected together rather than like 2. So they work in really large numbers. So let's take NaCl. That means you have 1 sodium for every 1 chlorine. Calcium chloride, on the other hand, has a 2. So there's 1 calcium cation per 2 chlorine anions. So the ratio doesn't have to be 1 to 1, depending on the charges of things. So here, calcium is 2 plus, whereas chlorine is minus 1. So to balance those, we need more chlorines than we have calciums. Which leads us to our last rule. The sum of the charges of the cation and anion in the formula unit have to add up to 0. So that's why our sodium and chlorine is 1 to 1. Plus 1 minus 1 add together to 0. But in calcium and chlorine, calcium is in the second column. It's going to tend to take a plus 2 charge. And chlorine is only going to have a minus 1 charge. So you need multiple chlorines to balance out each calcium. So there, with this ratio of 1 to 2, it's exactly balanced. So let's finish up this video by using Lewis theory to predict compounds and what those ratios will be. So I want you to try drawing a Lewis model for these. I'm going to do lithium and chlorine first, and then I'll let you do the other 2 examples. So lithium has 1 dot. Chlorine has 7 dots. So the easiest ratio is just to have one of these. 1 lithium and 1 chlorine lets that lithium transfer its electron here. So you end up with lithium with no dots and a chlorine with 8 dots. Now that won't always be the case, and I'm going to let you look at the next 2 examples. And just as a note, if you don't have enough electrons to transfer, add more atoms of the type you think that would help. So if you don't have enough electrons, add more metals to give electrons to the other things. If you don't have enough places to put electrons, add more nonmetals because they can accept them. So I want you to give this a try with KBr and then calcium and nitrogen. So now let's take a look. So KBr is another example that's just 1 to 1. So that one won't be too bad. You have K plus, sorry about that. So you have K, which is going to have 1 dot. I drew a very big dot for no particular reason. Bromine, again, has 7. So we're going to have this 1 dot transfer to that. So you'll have, this was plus and minus. So you have K plus and a Br with 8 dots, which is 1 minus. That means here we would predict lithium chloride and potassium bromide. Now calcium and nitrogen is not nearly as simple. Calcium has 2 dots. Nitrogen has 5 dots. So with 1 calcium, you're going to move 2 of the electrons, but you're going to run out before you fill up the nitrogen. So you can try adding another calcium with 2 more dots. But now you're going to add 1 more here, and nitrogen, you're going to run out of space. So you need another nitrogen. But now when the calcium adds an electron here, you run out of electrons. So I need a 3rd calcium. This 3rd calcium, though, will finish it up. We'll add 2 here and 2 here. So you end up with 3 calciums that are all 2 plus. And you end up with 2 nitrogens that are full, that are both 3 minus. So this means I would predict these would form the compound calcium 3, nitrogen 2. So these are my 3 predicted ionic formulas. Remember, it's not that there is exactly 1 lithium and chlorine, but there's a ratio of 1 to 1. With calcium and nitrogen, there would be a ratio of 3 to 2. So that ends our section on Lewis theory, and we'll end our stuff for this week. What we'll be moving into next is actually naming these compounds. So now that we know what an ionic compound is, the next part of this chapter is going to be look at how do we name something if we know it's ionic.